Okay, good morning everyone. This is coming through okay, correct? Super, so good morning to all of you joining us here in Belém today, and good afternoon, good evening, good night to those of you joining online. Today we've got some really exciting talks here in the Cryosphere Pavilion, all about the Southern Ocean, the changes that are happening there, and its impact on the ecosystems and unique creatures living in these habitats. So without further ado, I'm going to pass over first of all to Christopher Auckland from the University of East Anglia, who's going to give us an overview of the changes that have been happening to the Southern Ocean. Before second, we'll move on to Grant MacDonald from the University of Durham, who talk a bit more about the impacts on penguins and ecosystems more broadly. So over to you, Chris.
Thank you, James. So my name's Chris Auckland. I'm one of the early career scientists that's helping out with the Cryosphere Pavilion here. And I'm also got my University of East Anglia hat on as well. And so I'm going to be talking about the Southern Ocean in general, giving an overview of the physics and giving an overview of a couple of the changes that have been going on. So for those of you who don't know, we're going to start off very basic. The Southern Ocean is right at the very South Pole. So you think of Antarctica, and it is the oceans that are surrounding Antarctica and surrounding the large continent. So there are three main important points to think about when we're looking at the Southern Ocean. Number one is it's zonally unbounded. So what I mean by zonally unbounded is that we've got currents that are going all the way around the Antarctic continent, and it's one of the only oceans that the flow is completely unblocked. So we get these very fast, very strong currents whipping around the Antarctic continent. Number two is it's a global connector. And so what do I mean by that? I mean that we're linking together all of the globe's oceans. So we're linking together the Atlantic, the Pacific, and the Indian Oceans, all in this global mixing conduit around the Southern Ocean. And then finally, it's a very dynamic ocean. So it's actually defined by fluid boundaries, as it were. So you have the different fronts and the different physical front systems that define its northern edge and that define the Southern Ocean itself. So this is one way to look at the Southern Ocean. But one of my favourite ways to think of it is actually from a fisheye's view. So this is the Spillhouse projection. And what this really highlights is that we don't just have many different oceans, we actually have one global ocean with the Southern Ocean at its heart and Antarctica at the heart of this. So you can see here that we have all of these deep water masses, all of these surface water masses that all mix together in the different ocean basins. So you've got the Atlantic and the AMOC, and you've got the various Pacific Ocean overturnings, and they all return round to the Southern Ocean, and they all return around Antarctica. So let's think about some of the really important features that are in the Southern Ocean. And I mentioned before this zonal unbounding, this really fast current. And this really fast current is also known as the Antarctic circumpolar current. Circumpolar being, as I say, that it whips all the way around the Southern Ocean and whips all the way around the continent. It's very deep reaching, so it's barotropic, as we physical oceanographers call it. And what this means is that the flow is going all the way from the surface down to the very depths. And it's connecting these surface winds that are whipping and driving some of these currents down to the very bottom boundary, and the momentum that's put into the ocean by the wind is then taken out of the ocean by bottom friction. It's also topographically steered. Now, that's a bit of a complicated term, but what I would like to think of it as is we have all of these underwater ridges, all of these underwater canyons that are around the Southern Ocean's bathymetry. And what these do is they drive and steer and twist the current. And actually, it's a very important thing. This topographic steering is a way that we start getting some of our subpolar gyres, such as the Weddell gyre or the Ross gyre, as they're sheltered from the ACC. The ACC, whipping all the way around, it kind of acts as a barrier and protects some of these subpolar gyres, such as the Weddell Sea that you see between the peninsula that's starting to form to the east of it. And you start seeing this protection of these cold subpolar gyres from the rest of the ocean. And then finally, the ACC acts as is a way that the Southern Ocean acts as the lungs of the ocean. It's the way that we start to see upwelling of century-old deep water. And so this upwelling of the century-old deep water occurs in the ACC and is the way that we can capture a lot of the carbon dioxide and we can ventilate a lot of the oxygen into the deep abyss. Another key feature of the Southern Ocean is the sea ice. And you'll be hearing a lot more about the sea ice and the sea ice's impacts on our ecosystems and on the biodiversity around Antarctica, I'm sure. But from a physical oceanographer's point of view, one of the really important things that we're looking at in the sea ice is the way that it changes the buoyancy fluxes and the way that it shields some of the subpolar gyres, and it's the way that it interacts with our ocean, because this sea ice acts to protect it from air-sea interaction. So we don't have as strong air-sea interaction when we've got sea ice areas until it starts breaking up and we see these gaps in the sea ice called polynyas, where we start to get really intense convection, really intense heat and cooling. And as well as that, the formation of this sea ice leads to something called brine rejection. So it's a way that we input a lot of the salt, because when sea ice forms, it rejects a lot of the salt in the sea ice itself and puts it straight into the ocean. So it's one of the ways that we form these deep, dense waters. Not only that, the sea ice is a very dynamic moving system. So you'll have seen in this animation that actually there's a very pronounced seasonal cycle whereby in the winter we get these large sea ice extents, and then over the summer it starts melting back and we start seeing large sea ice free zones. And in particular, in the last decade, Antarctic sea ice has been in great decline and has actually been declining faster in the last decade than in the Arctic. So I've explained a little bit about these deep, dense waters. This is a bit more of a complicated slide, but we'll go through it together. So what I mean when I'm saying that there's upwelling and that the Southern Ocean is the lungs of the ocean is coming back to this idea of overturning circulation. So it's a two-cell system, and what I mean by that is that you have sinking of some dense waters around the poles, and these dense waters that sink around poles drive the bottom half of our circulation. So if you look at the Atlantic sector, you can see right there that we've got something called AABW that's formed around Antarctica, Antarctic bottom water, and it fills the bottom of the oceans. And similarly up at the in the Arctic, you have dense waters that form around the Arctic and then fill the abyss from there. And it's actually around the Southern Ocean, around the ACC, that these mix together, and that we see this upwelling of century-old deep water, and we see this creation of the newly formed waters around Antarctica. And it's a very delicate balance with the air-sea interactions, with ocean mixing. And it's, again, coming back to this idea of a mixing, a blender, a conduit for changes that can be communicated from one basin to the others. So talking a little bit about bottom water itself, and a shameless self-plug here with the figure, but we have these really strong ice-ocean interactions. So thinking about the sea ice, I mentioned you've got this really strong brine rejection where you're adding a lot of salt into the water, where when you've got these strong offshore winds, you get this sea ice formation areas, and you get a lot of ice-free regions, which allows something called deep convection. You get really strong cooling of these waters. And what this does is it creates really cold, really salty water. And this cold, salty water is actually one of the most dense water masses on the planet. And it's what we call Antarctic bottom water. But obviously in recent years, with these changes in sea ice formation, with changes in ice around Antarctica, we're starting to see a different mixture of waters that are forming on the shelves. We're starting to see a warming trend in this bottom water. We're starting to see a freshening of this bottom water as we start losing a lot of the constituent water masses that make up bottom water. And in fact, it's this slowdown in formation, it's this slowdown in export of bottom water that's starting to slow down a lot of these global overturning circulations. And for the most part, observations suggest that there's a strong role of sea ice and there's a strong role of warming of the constituent water masses that we're starting to see here. And talking of the bottom water in a global context, I mentioned that it forms the basis of a lot of the global oceans. And you can actually see in this figure, it's the abyssal plains, so oceans that are deeper than 4,000 meters, and the fraction of that that's filled by bottom water. And in the Indian, in the Pacific, you can see that Antarctic bottom water actually dominates the ocean basins right the way up through the northern hemisphere. The picture's a little bit more complicated in the Atlantic, with, like I mentioned, this Atlantic deep water that's formed around the Arctic that again, forms the bottom limb of this circulation, but you can still see it rising right the way up, almost to where we are up in Belém as well. As well as that, you start seeing these signals of warming within the basin. So I mentioned the warming of the Antarctic bottom water. I mentioned that it's starting to get shrinking in its volumes, warming, and you can see here that this warming signal is concentrated around the Southern Ocean. And we like to think about things such as sea level rise and the impact, the human impact of these things. We think sea level rise in terms of additional freshwater inputs, additional meltwater inputs, but we can also think about it in a warming context. We can think about just the thermal expansion of seawater, and in fact, it's very prevalent within the Southern Ocean. We're getting 0.5 millimeter per year of sea level rise just from the warming signal, not even adding any extra water. And finally, I'd like to explain a little bit about why the Southern Ocean is quite hard to study. So apologies for anyone who gets seasick looking at this video, but the Southern Ocean is what's something known as a data desert. And what that means is we've got all of these, we know that all of these large changes, all of these things are happening around the Southern Ocean, but actually trying to get out there and quantify it is very, very hard. Not only do we have sea ice to contend with, so we have to have these very expensive, very technologically brilliant ships that are icebreakers, such as the new British Antarctic Survey's David Attenborough, but you've got to contend with some of the most stormy, some of the largest seas on the planet in order to actually get there and take your observations of the ocean. And so just to highlight that in a kind of global context, on the right here you've got a map of all of our observations, all of the long-term observations we have, and you can see that it's actually relatively sparse in a lot of the Southern Ocean sectors. It's concentrated around where we have Antarctic bases, it's concentrated in certain sectors, but actually there's a relatively sparse observational system. On the right we have something called the Argo, which anyone who knows ocean science, these Argo floats are left in the ocean and can profile the ocean. But there's again a bias towards the non-Southern Ocean purely because of the sea ice and its remote and inaccessibility. You can see that there's so many Argo floats up in the Northern Hemisphere, but when you start reaching a latitude of around 60 south, it becomes a lot more sparse in the observing systems. So I'm going to end it there, but like I say, I just wanted to highlight how difficult and how hard-won observations of these changes that we're seeing are.
Thank you so much, Chris. That was incredibly informative and interesting to see the connection really between the Antarctic water masses around this polar continent and the rest of the world. So we'll take some questions for Chris later on, but I would like to now move on swiftly to our next speaker. So this is Dr. Grant MacDonald from Durham University, who is going to speak a bit about the response of emperor penguins to these changing Antarctic sea ice conditions that Chris said has really begun to plummet in the last decade or so. So over to you, Grant.
Thank you very much. Thank you, Chris, for that fantastic overview. And thank you to the ICCI for having us again. I'm sorry I can't be in Belém. But yeah, so my name's Grant. I'm a postdoc at the University of Durham. I've been working with other colleagues at Durham, as well as the British Antarctic Survey, and in the US at the Oceanographic Institution. And I'll be talking today about the response of emperor penguins to changing Antarctic ice conditions. So emperor penguins are, of course, an iconic Antarctic species. I mean, you just have to look at this picture to see why. They're a real symbol of Antarctica, and as well as that, they're an indicator species for climate change. They're kind of canary in the coal mine. They also form an important part of the Antarctic and Southern Ocean biosphere. And quite surprising, actually, there was a paper earlier this year that showed they might even help mitigate climate change in parts of Antarctica. So it's a really interesting paper that showed that penguin guano is an important source of climate-relevant aerosol particles in Antarctica. I should point out that study was based on Adelie penguins, but it could potentially apply to emperors too. On the right here, you can see a picture of an emperor penguin colony, and that's their guano spread right out across the snow and ice. So emperor penguins, live on fast ice all around the continent of Antarctica. There's around 66 colonies, we think. They like to be on the fast ice, so this is the sea ice that's right up against the edge of the continent, against the glaciers and ice sheets. You can see them there on some fast ice, and you've got a big ice shelf edge in the background, and that's giving them some nice shelter from the wind, and it will also be an area of ice that should last longer for them. Now, one of the key things about their habitat is we're on the very edge of their possible habitat. There's nowhere south for them to go. If that ice goes, they can't just migrate south. Once any further south, and they're onto the Antarctic continent. Now, something that's really useful about that guano, I showed you've got this big stain across the snow and ice, is it means we can observe them from space. We've learned a lot about emperor penguins from satellite remote sensing over the last couple of decades, which has allowed us to learn about colonies that humans have never visited. So as I said, there's around 66 colonies across the whole continent, and most of them have never been visited by humans. And you can imagine why. It's a hostile environment. They're remarkable creatures that live in areas that are very difficult for humans to visit. And we know from that research, as well as field studies, that they're already declining due to numerous climate pressures. So a study a couple of years ago showed a 10% decline in numbers across the continent between 2009 and 2018. And then there was another study that just came out earlier this year that extended that over a longer period up to 2023 for just part of the continent. And showed a 22% decline for those colonies. So, which is really, quite dramatic decline. That's over 1% per year, which is not good for the future. Now, that's for various reasons, not only to do with sea ice, but reduced prey availability as the ocean warms, the ice conditions change. Increased competition from other predators as they move into the area, lack of fresh snow. Penguins use snow to hydrate. Could also be increased disturbance and predation from other predators moving in to new areas, and due to warmer conditions, and also things like increased rainfall. Rainfall can be really bad for penguin chicks and stormiers. So the whole load of climate impacts affecting penguins before we even really get into sea ice breakout. Now, just quickly, Chris gave a really nice overview of the Southern Ocean. I just want to reiterate again, because I've been talking about sea ice repeatedly and glaciers. You've got the Antarctic continent here in the middle, where you've got an ice sheet and glaciers flowing off the edge, and then you've got sea ice around it. The penguins that I'm talking about are all around here, right on the edge, on this fast ice. And since 2016, as Chris alluded to, we've seen a real decline in Antarctic sea ice. Up until 2016, actually, it was quite stable, and maybe even increasing a little bit. But since 2016, we've seen records being broken multiple times across much of the continent. There is some variability around, but much of the continent has seen really dramatic declines. This is just the latest figure on sea ice extent. So you can see that 2025 is not the worst year on record, but it's well below the mean. Last year was even worse, and we've had other years worse than that too. So really, penguins have really seen some dramatic changes just in the last decade. Oops. And low sea ice can be really bad for penguins. It can reduce the abundance of key prey species. So, for example, in the 70s even, we saw there was low sea ice at a particular colony, and that colony declined by half because the mortality of males increased due to low sea ice extent. And it's the impact of those changing sea ice conditions on the penguins' prey, such as silverfish and krill. The other key thing about sea ice for penguins is that penguins need that fast ice that they live on to be stable until the end of December approximately for successful breeding. So that's something we've been looking at a lot. On the left here you can see where sea ice breakout has occurred at the colonies. You've got a glacier here, and then you can see this kind of brownish ice. That is where a colony is broken up. Now, if that happens later in the year, January, February, that's normal and okay for the penguins. But if that happens in early December, November, then that can be catastrophic for the breeding success of a colony. As you can see, the penguin chicks on the right look very different to the adults, and they're not made to be in the water. At this stage of their lives, they're supposed to be on the ice, dry. And if that sea ice breaks up too early, they'll end up in the water, they can drown, and we can see catastrophic breeding failure for a whole colony. Now, due to these changing sea ice conditions in recent years, we've seen this breeding failure take place at numerous colonies. So we saw an increasing number of colonies affected by early fast ice loss between 2018 and 2022. If you look at these maps here, or these coloured dots, are all colonies that were impacted by early sea ice breakout in that 4-year period. So there was 19 of 66 colonies in 2022, so that's almost a third who have experienced some level of breeding failure. 4 of 5, particularly in the central and eastern Bellingshausen, suffered breeding failure in 2022. And then recently 9 of our surveyed 27 experienced increased breeding failure over the period 2021 to 2023. And then in our own work, we've also been looking at this. So we looked at the Nords colony, and we've observed 6 early fast ice breakout events that would have likely led to a degree of breeding failure at this colony. And one of those was as early as September, which coincided with record low sea ice extent at the time. So you had a colony here, if you look at the left image, and at the end of August, and mid-September that ice broke out. So those chicks are way too young to be in the water, and it would have likely led to serious breeding failure. We also have been looking at another colony called Sana, and we saw similar events there, although not as early. Another real concern is late sea ice formation in winter could be a threat to breeding. So penguins lay their eggs in the Antarctic winter, and while adults go to forage, and that's when the chicks really start to grow. To do that, they need a nice stable platform of sea ice. If you look at this here, this is a radar image. In July, the penguins want this stable sea ice here, and where you see this little penguin emoji, that's where a colony should be. But at this time, it wasn't. The sea ice was still flowing. It was not consolidated, and there's no way for a colony to establish there. So we don't know what happened there. Maybe a colony eventually established, but it could have been delayed, which could affect the whole growth of the chicks. Maybe they wouldn't be ready in time in December. We don't really know, but late sea ice formation in winter could be a real threat to breeding, something we want to look into more. Now, as well as sea ice, glacier change could also threaten penguins. So there's evidence that glacier carbon is increasing due to climate change. And actually this month there was a paper that got quite a lot of publicity. Some debates about exactly what it meant, but basically a glacier was seen retreating faster, and the fastest has been recorded, according to authors. And these kinds of extreme events could be really disruptive for penguins because, as I said, the penguins like to live right next at the edge of the ice sheet. So the penguins are on the sea ice, but they're right next to the glaciers. If these glaciers move, that removes their shelter, could remove their size, could be highly disruptive. Also, icebergs that come from these glaciers can block access to foraging grounds. So as well as sea ice, glacier change can be a real threat to penguins. That's something that we've been looking at over the long term, to look how penguins respond to glacier change. So, for example, we looked at a colony here. There's a colony located in the 80s at this red spot at the Sanya colony. As that glacier moves northwards, the colony moves with it. You can see this red spot moving to the north as the glacier moves up. And then in 2010, this large part of ice shelf broke off, and the colony was no longer visible at its original site. It relocated to a different site, tried a few other sites, and eventually returned to its original site, and then abandoned those new sites. So basically, this calving event, this breakup of glacier ice, was disruptive for the penguin. We don't know exactly how it affected breeding, but it forces them to assess their location. Similarly, at Mertz colony, the colony again, as the red spot, moved north as the glacier went north. In 2010, there was a huge calving event at Mertz. The glacier tongue broke off. The colony was not present at all the following year, so clearly highly disruptive. Eventually, the colony returned, but had to go to another site that was not ideal for breeding, that was closer to the edge of the fast ice. Eventually, again, it split into two and was trying different sites, and eventually it returned to its original site. So again, this is something we have to understand better, something we're looking into a lot, but it's clear that glacier events are highly, glacier calving events and breakups are disruptive to the colonies. It's something we could see happening a lot more due to climate change. Now, speaking of glaciers and ice shelves, another thing that we find interesting in our own work and as well as some other people have looked at is colonies moving on to glaciers and onto ice shelves. So this had been observed at a handful of colonies before, but we found it happening at even more than we thought. So you can see here at the Sami colony, the black here is open. There's no sea ice here, apart from some very old thick ice that's kind of stuck there. But the colony is visible here on the ice shelf. We also see a colony moving onto an ice shelf and glacier here, even when there is sea ice. And if you look at this right image, this is the Akka Bay colony. You have fast ice, sea ice on the right, and an ice shelf on the left. And we observed throughout the season how the colony moved onto the glacier ice. Now, it was often thought that the colonies were too clumsy, not agile enough to get onto most glaciers. You know, they have quite often quite steep cliffs, and if you've ever watched a video of a penguin walk, you can imagine they're not great climbers. But actually, what we are seeing them going up there, the reasons for it are often quite unclear. And actually, if you saw the Secret of Penguins documentary, which I highly recommend, there was quite an iconic clip of penguins jumping off of this, which was at this particular site. Now, the predictions based on sea ice trends for emperor penguins are pretty depressing. In a high warming scenario, modeling simulations have predicted that 98% of colonies could be extinct by the end of this century. So by 2100, within the lifetime of a generation. So that's almost all the colonies, basically, apart from some potential refuge in the Ross Sea. So and that's primarily due to sea ice loss and the kinds of things I've been talking about: breeding failure due to early breakout, how sea ice affects colony prey. But what's important to note is that those same model simulations found quite a different outcome with 1.5 degree of warming. Now, even with 1.5 degree of warming, the situation for penguins is not good. The study predicts 61% of colonies are at risk of extinction with the Paris climate targets. However, that's still a big difference to 98%. That would see significant refuges in the Ross Sea and in the Weddell Sea, and some other colonies would also have a chance. So although things are depressing, there is hope. Now, I think I'm just going to leave that for time, but so there's a lot of, the key takeaway here is there's a lot of key questions for better understanding penguins' future. We need to do a lot more research to really understand how they're being impacted, and we also need to know more about what's happening with sea ice, and particularly the relationship between sea ice and fast ice. I just want to end on talking about how humans and penguins' lives are really interlinked. So as I mentioned, emperor penguins are canary in the coal mine for climate impacts. They're very far away from us. They live on a continent. They exclusively live on a continent that no humans naturally live on. But the ice losses that they're experiencing will ultimately affect us all in different ways. And what we do here in Brazil, in the UK, our choices and policies will impact their future. And although the outlook is bad for penguins, there's a lot of very concerning trends and predictions can be very depressing. There is still a lot of room to minimize damage if we take action. So thank you. I'm going to end there and would love to take questions and chat more. Thanks.
Thank you so much, Grant. That was really an excellent presentation. Really fantastic overview of the current circumstances of these penguins, also the peril they're facing under the future choices we're making here at COP30, but also ending with a message of hope there about the action that we can still do that can make a real difference. So I'd like to invite Chris back up onto the stage also before we open the floor to questions. So have we got any questions in the audience for either Chris or Grant? And perhaps while you ruminate on that, I can kick off with one for Grant first of all. So you talked about measures to conserve the populations of these penguins, but what conservation methods or measures would be best or most effective for protecting emperor penguins in the future?
Thanks. Yeah. So one thing that gets talked about with southern ocean conservation and around emperor penguins is marine protection areas. So marine protection areas could certainly be valuable, helping protect them from overfishing, both and being impacted by that directly, and the impacts of that on their prey, particularly at refuge sites, to make sure that those colonies that could survive as the climate warms are really protected. But really, by far the most important thing for penguins is reducing emissions and limiting climate change. There's really only so much we can do in terms of direct conservation measures. The real thing the penguins need is stable ice and stable climate.
Thank you so much. I'm going to pass on to a question for Chris first of all. So I really liked your description of the Southern Ocean as a desert of information and the need to really improve observations to make better predictions of these systems and how they might change in the future. Now, as you know, there are several major initiatives starting up over the coming years, so this year being the International Year of Glacier Preservation and kicking off the Decade of Action for Cryosphere Sciences. We've also got the International Polar Year coming up in 2032. So are there any particular Antarctic sectors you think should be a real focus for these observations to make the most difference in terms of our understanding of these systems and the need to understand them for the future of changes to the cryosphere?
Yep, thank you for that question. Another really important initiative that I'd like to draw focus to as well is actually the Antarctica in Sync program. And so you asked, are there any sort of specific regions around the Southern Ocean? Well, I actually think the Antarctica in Sync program is potentially one of the most exciting, where we're trying to get large national, international cooperation from all of the Antarctic programs together to observe the Southern Ocean in sync, to observe all of the Southern Ocean and have a connected sort of observing system. Because like I said, like I showed with that long-term time series, it's often concentrated in and around regions where we have larger presences. So you can see that the Weddell Sea is potentially one of the largest regions where we can study, and that's primarily because along the peninsula itself is where a lot of these year-round bases are. I think in terms of exactly where to concentrate the studies, one of the big new things that I think we're seeing pushing forward is remote sensing. So like Grant was showing with satellite observations, are really starting to play a key role in being able to observe changes, and also things like autonomous vehicles. So the British Antarctic Survey and the University of East Anglia are kind of pioneering using these gliders, these autonomous vehicles, to get into places where people can't go and to get underneath the sea ice edge, get in and around the sea ice, where actually in regions where we can't get there. And that's kind of observing the regions where it's hard to go, I think, is the main point. So not necessarily a geographic area as such, but more trying to observe that sea ice edge, I think, is quite important.
Thank you very much. Any more questions from the audience? If not, I've got a few more lined up for our wonderful speakers. So going back to Grant, you showed, is there a question here? Okay, super, 1 second. I'll just pass you the mic.
Español, ¿no? Can you contextualizarnos? Can you contextualize us? The information, because we already, yeah.
About the kind of penguins.
Yeah.
Southern Ocean, and also bigger changes happening to the oceans around Antarctica.
Yeah, and you speak about something about indigenous people? No, just penguins.
Just penguins.
Okay. Yes. Context. Can be now a little bit. Yeah.
Yes. While we just get a bit of context for that particular question, back to Grant quickly. So you showed this fantastic animations of how penguins have actually moved from sea ice onto ice shelves in Antarctica, and you may have seen a fantastic image in the Wildlife Photographer of the Year by Bertie Gregory, which was actually showing these penguins on one of these ice shelves, which is displayed in the UK pavilion here at COP30. So does this mean that these penguins can simply adapt to climate change by moving onto ice shelves, or is there a hard limit to how much they can adapt to climate change?
Thanks. Yeah, I'd love to see that picture. Really, this is something we need to understand more, and something that I'm working on with the group is, trying to see how common this is, the moving on to glaciers and ice shelves, and when do they do it, and why do they do it. But I mean, really, the thing is that it's certainly no silver bullet for the penguins. It's not something that can save them from climate change, and it might play some role at some colonies, but it's not going to be an option for many colonies to simply move on. As I mentioned, they're not agile enough. It's often simply not possible for them to get up. Even at colonies where they can get up, some years they won't be able to do it at other years. And in other ways, the ice shelf is not suitable for them year round. So it's certainly something we need to understand better, but it's unfortunately it's not going to save them.
Thank you very much. Final question I've got for you, Chris, is all about impacts of these currents around Antarctica and also the North Atlantic slowing down. And as some of you might know in the audience here, we have an event today at 2 o'clock here at COP30 in our pavilion, chaired by ministers of Iceland and Finland, talking about the implications of the AMOC slowdown for the rest of the world. But perhaps you can give us a quick preview of these possible impacts, both on the Northern Hemisphere, Chris, but also in other places more globally.
Yep, thank you. So, like I mentioned, it's these waters that are formed around the poles. It's these waters, like the Antarctic bottom water, that form the bottom limb of our global circulation. Again, you've got North Atlantic deep water that's formed around the Arctic, formed around Greenland, and these formation processes is kind of the reason why we're seeing these larger changes. You're inputting a lot of fresh cold water. You're changing the buoyancy of these of this water. You're changing how it's flowing. So you're starting to see in the North Atlantic, especially, a slowdown of the AMOC. So the kind of impacts that we're projecting is particularly in North Europe. We're going to see drastic cooling. So we're actually predict that the impact of this AMOC AMOC carries the heat. It's a large heat transport up to Northern Europe, and by slowing this current down, you're actually losing a lot of that heat transport. So you're going to see much colder winters. You're also going to start to see much different sort of scenarios, much different ecosystems. And again, this upwelling of deep water and these current systems, actually this upwelling brings a lot of the nutrients from the deep to the surface. So you're going to start losing some of this nutrient transport. So you're going to start changing the biodiversity around the oceans, not just in the North Atlantic, but around the South Atlantic, around some of the fishery regions around the Southern Ocean. And also another impact is you're going to start to see changes in weather patterns. So again, changes to these current systems aren't just going to be affecting the oceans, because there's a huge interplay between the ocean, between the atmosphere. So changes to AMOC. You might have seen sort of the climate action thriller of 2012, where you start seeing these more stormy weather across the northern hemisphere. But you'll also have strong impacts right here in Brazil from changes to the AMOC. So you'll get large changes in the atmospheric conditions. In fact, over the Amazon, recently there have been predicted changes, rather drastic changes to the rainfall amounts that you're going to see across the Amazon as well, due to these changes in AMOC.
Thank you so much. So any final questions from the audience? Thank you.
Hi, I'm Margot. I am a PhD student, and I would like to ask you maybe a little bit of a fantasious question. So, what ideally could make a big impact on ocean current preservation, and what we can realistically do today?
Thank you. I'll hand that one to Chris first of all.
Thank you. So, I guess the main kind of takeaway point that I would say is we want to look at doing our absolute damn best to meet that 1.5 degree threshold, because a lot of the changes that we're seeing, certainly in the ocean currents, certainly with the sea ice and the fast ice that Grant was talking about as well, are down to being able to preserve our cryosphere, to be able to preserve the frozen regions around Antarctica. And I think the number one thing that we know works is reducing greenhouse emissions. The number one thing to start preserving our cryosphere, start preserving the ice that the emperor penguins are on, start trying to protect these and mitigate against these current slowdowns, is to meet that 1.5 degree threshold. So we need much more urgent action and faster action if we're going to meet that threshold, because if we're not, we're going to see quite drastic changes, not just, as I say, to the ocean currents, but as Grant was talking about, with large changes to the biodiversity around Antarctica as well.
Thank you. Grant, do you want to say anything for this as well, comment on that?
Yeah, I'll just echo Chris, really. Just the key thing with all of this is limiting the warming and doing our best to get it to keep it down to 1.5, and if it's not 1.5, 1.6, every decimal of a degree matters. It's really trying to limit warming.
Thanks. Yeah, every tenth of a degree really matters for the preservation of the cryosphere. And I think it's a really nice place to end here on work which has come out before the COP by Climate Analytics and the Potsdam Institute, which shows that we can still reach the 1.5 degree limit even if warming briefly overshoots that and comes back down again. This will involve phasing out coal in the 2040s, gas in the 2050s, and oil in the 2060s, reaching peak temperatures of about 1.7 degrees for a couple of decades, and actually ending up potentially as low as 1.2 degrees by 2100. So action here by leaders who are gathering in Belém today really makes a strong difference. So let's keep pushing this message that we can still have a really positive result through drastically reducing our emissions starting this year. With that, I'll say thank you very much to our two wonderful speakers. Let's give them a round of applause. And thank you for those of you also joining online. Thank you.
Thank you very much. Good luck.